All right. So last time we saw a bunch of examples of direct proofs. Now here's some general rules for you to kind of live by with your proofs when you're writing them up. At any time, you can state an assumption from the hypothesis, an accepted axiom, a definition, or a previously proved result. Okay, what that means is when you turn homework into me, you are allowed to put in there, in class, example 5 says blah, blah, blah. So I can assume that and go on, right? So if you're wanting to say, for example, we showed even plus even is even, we did that in class. So you could say we showed in class even plus even is even, and you could just use that fact and move on, okay? Accepted axiom would be something like we said, when you multiply integers, it's still an integer. We didn't actually prove that, but I said you can just assume that. That's what we mean by an accepted axiom. Okay, so at any point, you can use that fact that integer times integer is still an integer. Okay, and definition, well, we've seen definitions, so you can use those at any time. All right, at any time, you can state a sentence equivalent to a previous statement. What that means, all that stuff we did with truth tables and logical expressions, that comes in here. We know lots of different formations, so if you have the statement not P and Q somewhere in your proof, it's not true that this and this, then you are perfectly allowed to rewrite it. Well, either this isn't true or this isn't true, because that's the exact same truth value. Okay, those are equivalent statements. So that's another way you can help yourself in your proofs. At any time, you can state a sentence. Translation is a tautology. So that would be like when we do cases, you can say, well, either the integer's even or it's odd, right? Duh, it's either even or odd. That's always true, okay? And that would be an example of like using P or not P, okay? And then breaking that into cases and using that. All right, that's allowed. Another thing that's a tautology is when we say stuff like, well, x minus 1 squared is greater than or equal to 0. It's duh, any real number squared is greater than or equal to 0. So you can use that at any point. Okay, then if you have shown that A is true and that A implies B is true, you can assume B. So what that means is, let's say you know that if A and B are even, then their sum is even. Well, then if you work and work and work in a proof and get these two things are even, you can automatically say, so their sum is even, and move on, because you have shown that to be a true statement, okay? So does that kind of make sense? All those rules, any questions about those? All right, so let's keep doing more proofs. The more you see them, the more comfortable you'll get. I'll try not to give you vertigo zooming in and out. Okay. So we've seen a little bit with using cases, but I want to show you some more ways you can use cases to save yourself time and effort. Okay. So here we have a problem. We're definitely going to want to use cases. We want to prove that for every real number, oops, should say X and Y. For every X and Y in the real numbers, the absolute value of their product is the product of their absolute values. Okay. So I want to do scratch work, but how am I going to need to divide this up to consider it because of that absolute value? What matters? What does absolute value care about? Yeah, if they're positive, negative, equals 0, right? That's going to make a difference. In fact, you can write the absolute value of X as a piecewise function. I don't remember if we've seen this in this class. So it's just plain old X if X is greater than or equal to 0. But what is it if X is less than 0? Negative X, because the negative of a negative is a positive, okay? So I need to split this into cases, depending on if X and Y are positive or negative. All right, so technically that would leave me 4 cases, but we're not going to need to write out all of them. So one of them would be X and Y are both positive. This is my scratch work. This isn't my proof. Well, greater than or equal to 0, actually. Okay. Then this is going to be super nice, because if they're both greater than or equal to 0, what happens when I multiply them? Yeah, still greater than or equal to 0. So we'll get the absolute value of xy equals just plain old xy. But absolute value of x is plain old x. And absolute value of y is plain old y. So we're okay. That is matching. Xy equals xy. Okay. What's another possible combination? Both negative. Yep. If they're both negative, what happens when I multiply them? It becomes positive. So absolute value of xy is just plain old xy. But what's the absolute value of x? Negative x. And what's the absolute value of y? Negative y. Is that still going to work? Is negative x times negative y the same thing as x times y? Yeah, so we're okay in that case. All right. What else is possible? Yeah, one's positive, one's negative. Okay. So then what happens when I do x times y? It's negative, or it could equal 0, but that's not going to be an issue. Okay, we'll see, right? Because if x is 0, technically I could get equal 0. But let me look at my piecewise function for a second. If x equals 0, okay, if I plug in 0 into my absolute value function, does it actually matter which part of the piecewise function I plug 0 into? Will it change my answer? No, because negative 0 is the same thing as 0. So actually, we can say the absolute value of 0, that is 0, and that is negative 0. So that's not a problem, okay? So I can come down here and say that the absolute value of xy is negative xy. And if x happens to be 0, it's still true. I'm still getting 0 equals 0. Okay, not a problem. All right. And absolute value of x is x, and absolute value of y is negative y. Does that case work? When I multiply that absolute value separately, do I get the same thing as when I multiplied then took absolute value? Yeah, because I get one negative and then the xy. So, okay. Technically, there's something I haven't covered. What is it? Yeah, so technically, I didn't leave much space, but that's okay. We don't need it. I haven't covered x negative and y greater than or equal to 0. But what can you tell me about that case? It's going to be the exact same steps as the one above it. My negative is just on the x instead of the y, right? So we can actually shorten that, and I'm going to show you how, into one case, okay? We can actually combine those into one case. And that's how you actually said it out loud when I asked you. You guys said, or someone said, 1 negative, 1 positive. You didn't actually specify which was which, okay? All right, here we go, proof. And remember, all you turn into me is the proof. That's all I need. Proof. Let x and y be real numbers. Done. Okay. I want to show that that equation is true. So case 1. Assume X greater than or equal to 0, and Y is greater than or equal to 0, then XY is greater than or equal to 0. Now remember, this proof is your argument to a jury, right? So you can assume that your jury knows basically what you know. So they know how to work the absolute value function. So you can come in here and say, so the absolute value of XY equals XY, which is the absolute value of X times the absolute value of Y. All right, case 2. Assume X is less than 0 and Y is less than 0. Then XY is less than 0. This means
then XY is less than 0.
oh, sorry, greater than or equal. Thank you. Should have looked at my scratch work. What was I thinking? Okay, this means absolute value of XY equals XY, which equals negative X times negative Y, which equals absolute value of X, absolute value of Y. You didn't have to write it out this way, but this is the most compact way to get all that logic in one. Okay, I started with the absolute value of XY and worked and worked and worked through my steps to get to the absolute value of X times absolute value of Y. Okay. Any questions so far? All right, so case 3, here's how we can combine stuff into one case. So look at my original statement. X times Y, absolute value of X times absolute value of Y. If I switch the order of X and Y, does it change the statement at all? No, right? It doesn't matter which one's positive, which one's negative. Multiplication does not care which one comes first, okay? So what we use then is a math phrase called without loss of generality. That means it's interchangeable. It doesn't matter which one it is. I'm just going to pick one, okay? What do we do in our notes? We picked X to be greater than or equal to 0. So here's how it looks. You would say WLOG. And that stands for without loss of generality. I guess I should write that out to the side for when you look back. Without loss of generality. Without loss of generality. Okay, could I use without loss of generality if I had a statement that dealt with X minus Y? Good, no, I couldn't because you can't switch the order, okay? But X plus Y, sure, they're interchangeable, okay? All right, so without loss of generality, let X be greater than or equal to 0 and Y be less than 0. Then XY is less than or equal to 0. Thus, absolute value of XY is negative XY is X times negative Y, which is the absolute value of X times the absolute value of Y. All right. Yeah, absolutely. That is so WLOG, WLOG, that's a commonly accepted math phrase. Now, in a super formal math article in a journal, they probably write it out. For all your proofs you're turning in for your classes, your teacher will know exactly what you mean. And that's commonly accepted. Yeah. Yep. So we've shown all the possibilities. So say, therefore, in all cases, absolute value of xy equals absolute value of x, absolute value of y. Done. Another option, and this one can even work with subtraction or something, is to use the word similarly. So you write out all your logic for case 3, and then you get to case 4, and you could say, well, similarly to case 3, and skip a lot of the justification and logic if all the words would be practically the same with slightly different algebra. Okay, so you can use that word as well, similar to case 3, you know, to save yourself some effort. All right. Any questions on that one? All right, cool. Next one. Two integers have opposite parity, then their product is even. What does opposite parity mean? Yeah, one's even, one's odd. Opposite parity, even and odd. Okay. I'm talking about their product, so does it matter which one's which? No. Now, if it was talking about subtraction, I'd have to technically handle both, right? Odd minus even is different than even minus odd, though they both work, okay, to come out to be odd. But since we're doing product, it doesn't matter. So I can use without loss of generality. So my scratch work then, let's call them A and B. Which one do you want to make even? All right, A even, B odd. So A is 2K, B is 2L plus 1. And if you're using LaTeX to do the nice L like that, it's the command \L, okay, ELL. All right. So what do I want to do with those? Multiply, because I want the product. AB will be 2K times 2L plus 1. What's my goal? Have that it's even. So I look here and say, oh, look, I do have 2 times, a bit of a mess, but 2 times an integer, right? So that's what I need. So I'm ready for my proof. Proof. We'll say suppose A and B elements of the integers without nope, I should say have opposite parity. Sorry. Suppose those have opposite parity. Then we'll put our without loss of generality. Who knew you'd be writing so much in a math class? All right. Suppose A and B and the integers have opposite parity. Without loss of generality, let A be even and B be odd. All right, so then there exist K and L in the integers such that A equals 2K and B equals 2L plus 1. Let's see, but this means, and now let's write out our equation. A times B is 2K times 2L plus 1, which we said is 2 times K times 2L plus 1. All right. Since K and L are integers, K times 2L plus 1 is an integer, meaning AB is even. All right. Any questions on that one? Okay, so I think the next one actually you guys might be okay with. I might want to jump over this, but if X and Y are odd, then XY is odd. How are you going to approach that one? How would you approach it? Yeah, do the definition of odd, right? I have a 2K plus 1 and a 2L plus 1. It wants the product, so I have to multiply them out. Okay, so we'll just do the scratch work for this one and then move on. So then we have 4KL plus 2K plus 2L plus 1. What form do I need to be odd? I need 2 times something plus 1. 2 times an integer plus 1. Well, if I factor a 2 out of those first few terms, oh, here, move that down for you. Factor 2 out of those first few terms and let the plus 1 hang out, I do have 2 times an integer plus 1. So that's the scratch work. Then the whole meat of this problem would just be writing it up in your proof, right? There's all your logic. The rest of the proof is setting up K and L are integers, you know, da 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 da. All right. Everybody okay if we just move on with that one? All right. So let's look at the next one. Yeah, because this one's a divides proof, and I wanted to get to another one of these today. So if 7 divides 4a, then 7 divides a. This one is going to require a little bit more tinkering than a straight divides, like that first homework problem you have. Okay, so let's do some scratch work. 7 divides 4a. That means 4a equals 7 times something. I'm going to call it k. Some integer k. Well, what would you like to claim about k? It's an integer. And looking at that, what do you think should have to be true about k? Okay, have to be rational. Integer is even more specific than rational, though. What happens if k is odd? Let me put it that way. What's 7 times an odd going to be? What's odd times odd? Odd times odd is odd. That's the proof we just kind of skipped, right? We did the scratch work. So, but 7 times k is definitely even, right? 4a is definitely even. So that means k can't be odd. K has to be even. Because if k is odd, I have even equals odd. That doesn't make sense. So k is even. So that means we can write k as, let's do 2L. All right, let's rewrite our equation. 4a equals 7 times 2L. Now I can divide by 2, get 2a equals 7L. What can you tell me about L? It still has to be even, right? Because 7 times L is still an even number. And if L were odd, 7 times L would be odd. So L has to be even. So that means L is 2 times M. So 2a equals 7 times 2m. Divide by 2, a equals 7m. Huh? Yes, but what's my goal? My goal is to get 7 divides a, which is what I have, right? So yeah. So it looks really, really similar all throughout, but that's because our hypothesis and our conclusion that we wanted are both very similar statements. Yep. So when you write up the proof for this, you cannot declare every single letter at the beginning. You have to declare them as they appear, okay? So the only one we can declare at the beginning is a. So let a be an integer such that 7 divides 4a. And then one by one, we're going to bring in our new integers. Then, so what was our next step? We said, then there exists k in the integers with 4a equal to 7k. But if k is odd, 7k would be odd, since 4a is obviously even. Since 4a is obviously even, k must be even. Thus, there exists L in the integers with k equal to 2L. Our equation now becomes so what did it simplify to? It became 2a equals 7L. Remember, you're allowed to skip a little bit of algebra if you feel like your audience could follow along pretty easily, okay? All right. Similarly, because we're going to use the exact same logic, L must be even. So there exists M in the integers with L equal to 2M, resulting in A equals 7M. Yes, what's your question?
You said our equation about 2a equals 7.
Mhm.
And that's the one at the bottom right there.
Yeah, so when I said our equation now becomes 2a equals 7L, I basically plugged in 2L for k and divided by 2. I just didn't write all that in. Yeah. Yes, no, absolutely. And your proofs are going to be your style. You put the detail you need that you feel like needs to be there for explanation. Different people are going to have different levels of explanation in their proofs. Okay, I'll let you know if it's ever not enough or if it's too much. Okay, I'll tell you. So, all right. The ergo, we haven't used that yet today, I don't think. Ergo, 7 divides a. Done. All right. So I don't know if all these appear in your homework problems I picked for this chapter, but there are some other definitions that appear, okay, that may come up. And if you're reading through the chapter, you'll see these if you're reading examples in the chapter. So I want to go over them. So for prime, our universe is the natural numbers. What do you think of when you think of prime? divisible by 1 and itself. So yeah, so prime, this is going to be, has exactly 2 factors. One and itself. So this does exclude 1 from being prime. We do not want 1 to be prime. That causes issues. Okay. With the fundamental theorem of arithmetic and stuff, that causes issues. So 1 is not prime. All right. Composite. Still, we're going to let our universe be the natural numbers, though you could make it the integers. What would composite mean? Okay, not prime works except 1 isn't composite. So you could say not prime and bigger than 1, not prime excluding 1. Another way to say it would be to say it has more than 2 factors. Those mean the same thing. Okay, so I'm going to write both. So has more than 2 factors. Or you could say it's not prime and greater than 1 would be another way. Those mean the same thing. Those give you the exact same numbers. Okay. Greatest common divisor. Notation for that is that weird GCD parentheses with A and B in it. Normally, again, your universe is natural numbers. Sometimes they'll extend this to the integers, but typically natural numbers. What is the greatest common divisor? What do you think? It's the largest divisor they have in common, right? I mean, so it's the largest number that divides both. Okay, so that would be the words. Largest number that divides both. There is a way to put that in symbols. You can say the GCD would be if for every C, such that C divides A and C divides B, C is less than or equal to D, right? So I guess I should say D equals your GCD of AB, imply if and only if for every and I should add and D divides A and D divides B. Okay, so D divides both A and B, and anything else that divides it is smaller than it or equal if he's the same thing. Okay, that would be a symbol's way of saying it, but it's the largest thing that divides both. Least common multiple. Is the smallest number both A and B divide into. Okay. So, like I said, for this homework, I don't think I put anything on there that has these words, but some of the examples in the book have them, you know, and you want to be familiar with the definitions. We will use these more and more. Okay. And then at the end of the notes, I just put down a couple statements the book proves that I don't know if you'll need these for your homework, but since the book proved them as full examples, you are welcome to use them in the middle of a proof. So like this first one, if x is odd, then x squared is odd. The book proved that. So you can, in the middle of a proof, you can even reference it if you want. You could say book example 4.1.3 or something, you know, odd squared is odd, something like that. So, all right. Any questions on that direct proof stuff? All right. Let's see.